here's how we're going to do. The idea is that we're going to classify our image points based upon computing that Harris matrix and looking at some measure that's a function of its eigenvalues. And the idea is that in a flat area, both of those eigenvalues would be very small. In fact, if it was perfectly flat, everything would be 0 because the gradients were 0 everywhere. And that would mean no matter how I moved, nothing changes. So it's a terrible corner. Likewise, if I have just one of the eigenvalues large, that means there's some direction that it changes quickly. So if I move in that direction, I know things have changed. But if it's 0 in the other direction, I can move as much as I want. Remember, that's what happened along an edge. So when one eigenvalue is much, much bigger than the other, then you're along an edge here. And when is it a corner? Well, when both of the eigenvalues are large. And we'll say that it says here that they're approximately the same magnitude, just that they're both big enough and that the ratio between them should not be terrible. Right? Even if they were both large, but the ratio between them was 10 million, then probably your code was wrong. If they're moderately large and your ratio between them is still pretty big, then you have to worry because it means one gradient is much, much more dominant than the other, and maybe the noise is affecting finding of the corner. So you want them to be approximately the same magnitude. So you might think, great, that means all I have to do is find the eigenvectors and the eigenvalues. Right? Right. Guess what? You don't even have to do that. This is what was so good about the Harris thing.